Oh, is the camera plugged in? Can you check, please? Yeah, check the extendo cables. It's not plugged in.
Yes,
it's not plugged in. Just
it's plugged in.
Unplug and replug then. Fucking plug it. Please, for the love of fuck. There we go. We're back.
We're back. All right.
Yeah, we should be back. Sorry, guys. More technical difficulties. Eventually, my computer should stop dying. We should have solved everything now. Lamar, let's continue.
So the next thing we're talking about is the ALU. And the ALU is a combinational circuit, which means the output is a function of the current inputs and nothing further. It doesn't remember anything from last time. It doesn't have any like state hidden away anywhere. It's just essentially a great big. You can draw a truth table for the operation of this thing. And so it's got two inputs, A and B. It's got an input for the operation, sometimes called the op code or the operational code. And it's got a result. The result output is at the bottom, and it's got a flags output on the side. So all this is, the ALU is essentially a calculator, more or less. You insert two numbers into the A and the B inputs. You specify what operation you'd like it to do, addition, subtraction, logical and, multiplication, if your ALU supports it, which it does on the dev board. So you give it some operation here, and, or, plus, whatever. You get two numbers here, A and B, and you get the result on the output. So if I ask the ALU to do the operation addition, then the result on the output will be the sum of the two inputs.
So I might just cut you off for a second there, Dave.
Sure.
I think we've kind of segued a bit into 1V, which is briefly describe the fetch, decode, execute cycle.
Not really. I'm describing the ALU. I haven't really talked about fetch, decode, execute yet.
But yeah, we're about to get to that.
We'll get that.
There's a big problem with glare on the monitor right now.
Oh, fuck.
I want to solve that.
It's all good. I'll shut some lights.
Yeah, Jen, we'll worry about it. The secondary output from the ALU are the flags. And the flags are things like, was the result of the previous instruction 0? Was the result of the previous instruction negative? These are called flags. So we've seen these before when we program ARM, right? Like the 0 flag, negative flag, overflow flag, carry flag. These are status flags that the ALU trips up when something interesting happens. So if we want to check when two registers have the same value, we can do a subtraction, and if the result of that subtraction resulted in a 0, then the 0 flag will be set, and then we can, conditionally branch on that. So at the end of the day, the ALU is really nothing more than a calculator, and it's the rest of the parts together that makes this thing a computer, not a calculator. And okay, that's what ALU is, the decoder and the sequencer. So the decoder sequencer, when the CPU fetches data from memory, so I look at my place in memory, I pull some bytes out, I need to know what do these bytes represent, right? So you might remember in like lab 2, we talked about like writing instructions from scratch as like bit patterns. This magic box here is the box that takes in a sequence of bits and works out what instruction does this represent. Is this a branch? Is this an add? Is this a push or a pop? I don't know, right? That's what this box is designed to do. And the control unit is essentially like the conductor of the orchestra. It's his job to tell the rest of the parts of the computer whose turn it is to talk and when. So the control unit is just directing all these other things to talk to each other. Because most of the parts in the computer are linked by a central data bus, if you have two people talking on the bus at the same time, the result will end up being garbled, right? Because they'll end up talking over each other and the signals will get mismatched. So we don't want that to happen, and the control unit ensures that won't happen. ALU, registers, control unit, decoder, I believe that's all the parts in the CPU as far as we're concerned in this course. There's other things like a cache, which is fast memory, but we don't cover that in this course. I feel that's like a pretty adequate description. Let's move on. Briefly to describe the fetch, decode, execute cycle. How does the CPU know where the next instruction to be executed is located? Okay, so first off, fetch, decode, execute. Okay, so the computer operates on these 3 cycles: fetching the instruction, decoding the instruction, and executing the instruction. And it does these 3 steps every time a single instruction is executed. So I'm going to briefly go through how these things work. So the RAM has got data pins and address pins. And the RAM is essentially nothing but like a really, really big lookup table. So you specify to the RAM, please give me the data located at 0x200000, whatever. and the RAM goes, all right, here you go, and it gives you a byte of data. So when we do the fetch, one of the registers, namely the program counter, will point to the address bus on the RAM. So the program counter tells us where's the next thing I'm going to fetch from memory. We fetch that thing from memory and we store it in a temporary place in the decoder. So we have basically the address going along this bus here. Please get me the thing from this address. And we take that piece of data and it goes into the decoder. So we've fetched our data. I don't know what it means yet, but I've just fetched some data from memory and that's all I've done. The second thing we need to do is we need to decode that instruction. So the control unit tells the decoder, please work out what this instruction means and tell all the other parts of the computer to act appropriately when we execute it. So I fetched some sequence of bytes from memory. This could represent any one of a number of instructions. That's what the decoder does. It works out what instruction this represents. So for example, suppose I fetched a sequence of bytes and those sequence of bytes were the instruction, I don't know, add R0, R1, R2. It's the decoder's job to work that out. And so once the instruction is decoded, I actually need to do what the instruction tells me to do. And that's what the execute part of the instruction is. The execute part of the cycle will do any one of a number of things depending on what the instruction is. But if we can consider what the add instruction will do, I want to take the result in this register, R1, and the result in this register, R2, add them together and put the result back in R0. So the control unit will tell the registers, please copy R0 into one side of the ALU, sorry, R1. So R1 will go here, R2 will go here, and then the result, which is R0, will be stored back into the R0 register in the register bank. In principle, how this is done with a set of multiplexers. Multiplexers are essentially like little switches. So you can imagine in a very simple computer with very few registers, you might have they're not physical switches, they're like, transistors in the day. We'll just pretend they're switches. I've got register here, R1, register here, R2. What's a nice way to do this? You just draw it like this. A bit of a simplistic way. But the control unit essentially controls these switches here. And so if I want to add R1 to R2, I'll put R1 in one of the inputs, and then flick this switch over to get R2 in the other one of the inputs. And the result will then need to be transferred to R0. And so depending on what this instruction is, we'll tell the control unit what things to hook to what. If we were doing something like a branch instruction, well, a branch is just modifying the program counter to tell the program to go somewhere else. So the control register would then modify the program counter and add some number to it or load some number into it or whatever. So execute could be really any one of a number of things depending on what the instruction is. After the instruction is executed, I need to know where's the next thing I want to execute. So if I've run this line, I've executed this instruction, and then I wanted to do the next instruction, which is branch to some label, I need to know where this lives in memory. So by default, when you have a piece of code in memory, it's stored contiguously. That means the next instruction after this one lives right next to it in memory. So if we look at what memory looks like, I've got some sequence of bytes. I don't know the encoding of this instruction, so I'm going to make up some random bytes. So this might be my add instruction. And then the very next sequence of bytes, some other random numbers, this will be my branch instruction. So how do I know where the next instruction lives in memory? That's what the program counter will tell me. If I take the program counter and add to it the size of this instruction, usually 4 bytes, sometimes 2 bytes, I will jump to the location of where the next instruction is located and then execute that too. So fetch the instruction, decode what it is, and then do what it tells me to do. That's what fetch, decode, execute does. After that, you increase the program counter a little bit to find the next instruction, and then you do it all over again. Fetch, decode, execute, fetch, decode, execute, and the computer will continue doing that indefinitely until I guess you yank the power or turn it off or an interrupt happens or any one of a number of things.
So I guess we've basically covered these 3.
I've covered these 2. I haven't really covered this one.
Stack pointer and linked register.
Yeah.
Okay.
Cool. So what is the stack pointer and what is a link register? Well, before we talk about that, we need to talk about, well, what's a stack? So a stack is essentially a magic scratch space in memory where you can put things and they'll be remembered for next time. So you can always just write some data to an arbitrary place in memory, but you don't know if that place in memory is already used up by some other piece of code. So how the stack works, it's essentially like a pile of pages on my desk, and I can always put more paper on top of the pile, and then when I want to retrieve data from it, I usually take it off the top of the pile one by one. You can read things from the middle of the stack, but that's not usually how we use it. We usually stack things on top, and then the thing on top is the first thing we take out. So we call it a first in, last out data structure. The first things that are put in are the last things that are pulled back out again. And the stack is just a contiguous block of memory, and the top of the stack is denoted by the stack pointer. The stack pointer is a special register that just tells me where in memory the top of the stack is. The top of the stack, this is a bit of a lie because it grows backwards in memory, but you can imagine the stack growing higher, and I put more things on top, and the stack pointer will go up. Imagine the stack growing smaller when I take things off the stack. In reality, it's backwards because the stack starts at the end of memory and grows backwards, but we'll gloss over that annoying idiosyncrasy for a moment. So my stack pointer may contain some number. Let's suppose it starts at 0x200. I actually don't know where it starts, but I just pick a random number.
Let's start with multiple zeros.
It's a bunch more zeros, but let's pretend it's 0x200 for pedagogical purposes. So whenever I push something onto the stack, so suppose I'll push R1, and R1 contains the number 3. So this memory address here is 200. I'm going to store the number 3, which is 0x00000003. And then the stack pointer goes up by 4. In reality, it actually goes down, so I'm actually going to draw it correctly what it does. Oh, I can't hexadecimal numbers that fast in my head. X1, F, A, B, C, D, E, no, B, I think. There we go. So the stack pointer will change from 0x200 to 0x1FB because it goes down by 4, because we added something to the stack. You like to think of the picture of it growing up, and in reality it actually goes down. So all the stack pointer does is it remembers for me where the current top of the stack is, and that's the thing that I will get if I pop something off the stack. Does that adequately answer what the stack pointer is, I would hope?
Yeah, and link register.
Link register. Okay, so when you call a function, when you branch to a subroutine, you can never really get back to the code you were at because you don't know where you came from. So if I've got some code, what can I get rid of?
Just try and use that frame because this one isn't focusing well.
Okay, I'll try to stay on this side. No worries. So I've got some code, main, do some stuff, branch to foo. And then foo has got some stuff. And then each of these instructions has got some address in memory. So suppose this is address 0, 4, 8, 12. And then over here, this is like 100, 104, 108, 112, whatever. If I jump from here to here, the program counter will change from 12 to 100 because the program counter always remembers the address of the current instruction you're about to execute. Which is an awful mouthful, but all it's telling me is that it keeps track of where the current code is, where we're currently executing code. So here's my program counter. Start here, 0, execute the next line, 4, execute the next line, 8, execute this line, 12, and this says branch to foo. What this instruction actually does is it takes the address of the first instruction underneath the label foo, that is this instruction here, and copies its address into the program counter, which in essence just makes program flow jump or branch, that's why it's called branch, somewhere else in the code. Problem is, if I'm done with foo and I want to go back to main and keep doing stuff, I forgot where I came from, right? This is why we use branch with link. So the problem is that if I want to remember where I came from, I need to hide that information somewhere, and that's what the link register is used for. So if the program counter is currently at 12, and I execute the instruction BL foo, that is branch with link to foo, the current value of the program counter, I lied a bit, the next instruction after this one, so which would be 12 plus 4 is something, 16, I hope. It's got some other instruction here. I store the instruction of the next thing after this, which is 16, in the link register, and then I jump to line 100. So the program count is modified, and the program goes whoop, and jumps up to here. And then I execute all this code here, which is whatever it happens to be. And then when I execute BXLR, that tells the computer to execute the instruction, copy whatever was in the link register, that is, copy the value I remembered, back into the program counter, which will take me back home again. So I take this 16 that I hid away, copy into the program counter, and I go broop, and jump over here, and then I keep executing the code. Now the reason why you want to copy the instruction, not this one here, 12, but the one afterwards, is because if I branched back to 12, I'd immediately get stuck in an for loop. I'd branch back to foo again.
Go back to foo, yeah.
So the brancher with link copies the next instruction, not the current instruction.
So it copies the PC, because
Yep.
PC contains the next.
Question?
Yeah, so what's in LR after you've branched back?
So branching back doesn't actually change the link register.
Okay.
Yeah, it's still, so after you branch back here, the link register will still point to that. The next time you branch with link, of course, it'll get overwritten. Yeah.
Alright.
So, I may in fact, oh cool, everything's like actually working.
Do you want to go through an example of this? And we can step through it and watch the
G'day.
registers twiddle.
Registers, okay, coolio. So here's my nice little like real simple demonstration program. Let's go for a step through. So just remember, no ops are do nothing instruction.
Is it possible to flip the screen around so everyone else can see too? Or?
Not trivially, no.
Oh, alright.
Okay, so I've put 1 into my register 1, and we're going to add R1 to R1, like, whatever short. It's now equal to 2. And here comes the fun part. So we've just executed this no op, and now the CPU has paused. And the program counter is pointing at branch with link to my function. So if we notice the program counter here, whole bunch of stuff, 1D2. So 1D2 in our case is line number 14.
Register with a link
Yeah,
register.
and the link register is pointing somewhere. Now, when we do our branch of link, you'll notice that the link register is now 1D7. So 1D7, that's going to be, what, the address of line 15, I suppose.
Yeah.
Yeah. So we've saved our sort of like little signpost telling us where to go when our function's done. Because the program counter is somewhere completely different now. So we'll do our little subtract, and now BXLR. So we're going to branch back to the link register, which, as we worked out before, is going to be like this no op here. So I'll step again, and we're back. And now we're just happily stepping through our program again. And we'll spin around in a circle, and yeah, it just keeps calling this function, and looping around, calling it again.
So the link register is essentially a breadcrumb trail, so that way you know where to come back to after you've called a function. Now, if you've got functions calling other functions, then you'll overwrite your link register and you'll forget where you've came from, which is why we have to push and pop the link register if we've got nested function calls.
Yeah.
Alright?
Cool, okay. Let's have a look at our Examarino. Okie dokie.
Yeah. So what are the roles in the context of making multiple function calls? So you need the link register to know where to come back to, and you need to push and pop the link register onto and off from the stack.
Yeah.
And the stack pointer keeps track of the top of the stack.
Yep. In principle, you could store the value of the link register anywhere. You could put it in other registers if you wanted,
Yeah.
but it's just convention to push it to the stack
Yeah.
and then pop it from the stack just before you branch back
Yeah.
to where the link register was pointing.
Yeah, so actually I noticed a few people doing this in their assignment. Actually, they would just store the link register in some other register. While you can do this, it's not really good practice. Because, well, then you don't have a register that you can use because it's holding a link. And,
Especially if you've got a nested function calling itself 10 or 20 times over. At
Yeah,
some point,
right.
you're going to run out of registers.
Also, if we're following function calling convention, then we'll probably have to push something to the stack anyway. But yeah, so should we draw something on the board very quickly to talk about the saving the link for nested
would you
function?
like to?
Nested calls, sure. Okay. Time for a real nice and simple example.
Wait, photo.
Oh, g'day, hello.
Hop out of the way, John.
Print screen now, everyone.
Yeah.
Yeah, print screen now. It's going away. All right. Let's have a very simple, not programmatic example. I don't know. Let's draw a little house or something. Ooh, that's a nice house.
Try again, John.
Okay, there we go. Yeah. Ooh, I could totally draw really good. And what am I for the last one? I don't know. Let's like draw a little tree or something. Okay, sure. Cool. Let's call this the 2219 house. Okay, let's call this the 2300 house. And let's call this the tree of life or something. I don't know. Okay. So you're in the 2219 house and you decided, right, I want to go over to the 2300 house for a bit. But so I know how to get back home later, I'm going to leave a little, breadcrumb trail, which I'll also just happen to call my link register for, whatever reason, that points, kind of back here, right? So here's like, a little happy old me going from my 2219 house over to the 2300 house. Now, while I'm in the 2300 house, some smart cookie says you should go and visit the Tree of Life. So I'm like, okay, cool. I'm gonna get rid of my old link register because I've only got enough memory to, hold one way back home. So I'm gonna now make it point over here. So I'm at the Tree of Life. And I'm done at the Tree of Life. I've received some holy wisdom from his freshness. And I've returned to the 2300 house. Now the problem is, I've only got one link register, and I use that so I know how to get back from the Tree of Life to house 2300. I don't know how to get back to house 2219 now, so we have a bit of a problem. So the way we get around this is that when we're here, and we know that we're going to need to go somewhere else as well, we take this link register here, and we push it onto a stack. So I'm going to pretend I have a little, like a little chest or something. Let's draw our little chest down here.
Rounded down
with our little lock on it and whatever. Our little chest. So I'm going to push this link into our little stack chest in here, right? So we're just going to drop this in here. Old LR. Okay. And now we're going to come back here. Cool. Okay. So I've gotten all the way over to my little Tree of Life over here, and I've came back to 2300. Now I don't know what my link is because I've just deleted it, but that's okay. I can pop it out of my little, stack chest down here. I'm going to grab this back, whoop, and cool, we're back. So now I know how to get back, to my original location. So yeah, this is basically how nested function calls work. Every time you go into a function, and you're going to need to go another function deep, you just push your link register to the stack, and when you come back from your, sub function, you just pop it back into the link register. And you can do this as many times as you need until you run out of memory.
So what's a typical function look like? Write down for us the typical.
Okay, sure. So I don't know, a really classic example, say from assignment 2, you might BL play wave.
And then playwave might call the BSP
then,
on your write function.
Somewhere down here. Play wave will, do some stuff, and then BL, BSP, whatever, yada yada yada. And then some more shit, and BX. Am I still in frame?
Yes, you are still
cool.
in frame, but I think you are missing something around that BL.
Yeah, we are, right? So we haven't actually saved this original link to get from play queue back to here, right? Which is going to be a problem, because when we branch with link here, this is going to go away. And we'll have another link back here. When we go to return from play wave, we're just going to jump to play wave again. No, sorry, we're going to just jump back to literally here. Yeah, that's just going to spin around in a circle. Yeah, so we're missing our pushes and pops of the link register. Usually you just want to do this right at the start of the function. So we'll go push. Squiggly bracket, yeah, nice. And another squiggly bracket. Cool, and then pop it.
And that ensures that you restore your breadcrumb trail.
Yeah, right. So our original link register is kind of, from here to here. And then with this push, we save it on the stack. So when we nuke it back here with our little, BL to BSP, whatever, and come back here, that's okay, because when we come down to this pop, we actually restore our like little breadcrumb trail all the way back up here, and we return to where we actually want to go to. So yeah, nested function calls.
Is there anything that changes the stack and is going to mess up pushing and popping your load?
If you've written your program correctly, as in like without any bugs, you shouldn't have any problems.
So you could like push and pop other things in between, as long as the number of pushes balance the number of pops.
Yes.
So if you like push one thing and pop two things, you'll like gobble up your link register, and then you'll like pop random junk into the link register, jump God knows where, and crash your program.
Yeah, so yeah, as long as you do everything in order.
And the dev board won't be.
We can push two registers in one time, and we can write them in one instruction. So what is the order of that?
I've had this question before, and I can't remember off the top of my head. So, yeah, you can push and pop multiple things at once. So you can do something like push R1, R2, R3.
So Felix the Great has just informed us that's equivalent to pushing R1, then pushing R2, then pushing R3.
So
Which is what you'd hope, right?
I think the push is in the order it's written, and the pop is backwards.
Yep.
Yep.
Yeah.
Yeah, that's right.
Okay.
You don't have to reverse the order yourself for the pop. You write it in the same order. As someone
So
else can.
that will do exactly what you expect to do. It'll push these and it'll pop these. If you just write this, it'll always do the sensible same thing.
Yes.
Now,
Push
this
R4.
is functionally equivalent though to saying push R1, push R2, push R3, and then pop R3, pop R2, pop R1. So yeah, if you're gonna do multiple pushes and pops, I would advise that you just do them like, if you're gonna do multiple at once for a push, also just do them at the same time for a pop. That'll make your life easier. Now, well, probably like the one exception for this is that if you wanna, I don't think there's any time you'd be doing multiple and want to get something out early. Yeah,
Can I suggest, as a lot of people like in the assignments and stuff were saying they're running out of registers to do computations, and this is a way that inside a function, if you need to free up a few registers just to do some computations, you right at the start of the function you push them onto the stack, like R2 and R3, then you can use R2 and R3 for whatever you like, and then right at the end pop them back. That way you get yourself a couple of extra registers to use in that function.
So you can treat the stack more or less like an arbitrarily large amount of like extra scratch space where I can dump things that I don't care about now, but I want to not throw away and use
It's
again
that
later.
closet full of clothing in your room that you just keep shoving stuff into when it's not laundry day yet, but you can't be bothered to do it. So if you need a few extra registers and you're not using them immediately, like you can just push a few, use them to do your calculations and stuff, and then when you don't need them anymore, get the original values back, just pop and you're there. Next question, Dave.
All right, let's move on. So question 1D is you're given some constraints below the blah, blah, blah you must satisfy. So we're trying to do certain operations using only logical shifts or logical bitwise operations.
Yep.
So the first one is that assuming that there's a 5 in R0, make R0 contain a 10.
Okay. So R0 equals